Okay, our next section is on graphical summaries of observations or graphical summaries of our information that's in our sample. Now, I really like doing graphs or plots because it can help you understand or give you an initial picture of what your sample is representing. And then after you do a more sophisticated statistical analysis, then it will help you make sense of the inferences that you're actually making. So I always try to include plots, graphs, and anything that I do to provide a better picture of what's going on. You know, if you've ever heard the phrase, "a picture is 1,000 words," indeed, doing plots, doing graphs can really help you make sense of what is going on with your data. Now, especially in an introductory statistics course like this, graphs, plots, I use those terms interchangeably, can help you can help you learn these inference methods that we're going to be talking about. And so throughout the rest of this course, I will be using lots of plots to help you understand the material. Okay, so to begin here, we're going to take a look at actually something that's not a plot. It's actually a table, and it's called a frequency distribution. So a frequency distribution is a summarization of the observations in terms of the numerical values into classes or groups where the number of observations per group is given. So for example, if we take a look at this wind speed example that we've seen previously, one could go through the data, and I'll show you how to use R to do this in a little bit. One could go through the data and see that between, in terms of wind speeds greater than 2 miles per hour and less than or equal to 4 miles per hour, there were a total of 6 observations that had that. There were 22 observations that were greater than 4 and less than or equal to 6 miles per hour. Now, on the far right side here, we also have what's called a relative frequency distribution. And all this is now the proportion of observations that fall within a class or a group. So this 0.04 here is 6 divided by, I think we have 142 different wind speeds. So it's 6 divided by 142, which is approximately 0.04. And so what this table is showing us with respect to the wind speed example is that typically in Lincoln, wind speeds are between about 4 and 12 miles per hour. But we also see is that we have some, oops, I'm going to redraw that. We do have some more extreme situations where we can be up to about 24 miles per hour in terms of the average wind speed. And so what we see here is, we essentially, let's say, go up fast in terms of our wind speeds, in terms of the lower classes, and then we kind of go down slowly for the other wind speeds in terms of these frequency counts. Now, a better way to actually see that is through a plot of this frequency distribution, and that's essentially what a histogram does. It's sort of like a bar chart where the bars represent, or the height of the bars represent these frequencies. So let's take a look at how to do this in R. So let me get my tin out. Okay, so we've already have the wind speeds in R. They're in this data frame called wind. So there we go. Let me actually do a head on it. So remember, we have 5 years worth of information. We have the daily wind speeds. So we have day 1, 2, 3, and then Y is the actual wind speeds itself. Okay, so to do a histogram of these wind speeds, simply we use the function hist, where the first argument happens to be called x, just to be kind of generic, and this is where we put the wind speeds. So we pull Y out of the data frame wind, and we're also going to say, well, I don't need my bars to be colored at all, so let's put COL for color equal NA, meaning don't show any color. The default would be to use a color of gray. And unfortunately, this opened up in a different window. Let me pull it over here. And here's our histogram. So for example, between greater than 8 miles per hour and less than or equal to 10 miles per hour, we have a total of 29. So that's how far that goes up. If you see where my mouse is, we have a frequency count of 29. And then we also see what I was trying to describe with the table, that in terms of these lower wind speeds, it goes up slowly in terms of the frequency counts. And then eventually we reach our peak. I'm sorry, let me restate that. These frequency counts go up fast relative to these wind classes. And then it goes down kind of slowly and eventually gets down to about 24. And when we see something like this, we can see that the distribution is not symmetric, meaning that there's not much on, let's say, the left side of what we think of as the middle in terms of where we have the highest counts, but there's a lot more stuff on the right side of the distribution in terms of the number of classes that fall there. And we will relate this to something shortly that we call skewness of a distribution. So again, and sorry, I should have brought this up at the very beginning, we have wind on our x-axis, we have these frequency counts on the y-axis, in case that wasn't clear. Okay, let me get back to my notes. Okay, so that's essentially about the default of what a histogram will look like in R. Let's see if we can make it a little bit nicer. And so to do this, I'm going to use the hist function again. I'm going to again plot these wind speeds. For my main argument, this allows me to put a title on the plot. So daily wind speeds for Lincoln. X-axis label, xlab, wind speed. And then also I'm going to control where the limits on the x-axis are drawn. I want to go from 0 to 25. So the minimum value, the maximum value, and I combine them together. We saw something very similar when we used the plot function in our introduction to R section. And lastly, what I'm going to do too is I'm actually going to open up a new graphics window to display this graph. I don't have to. By default, if I were just to execute this code, it would go to the same graphics window that we just had. But just to show you that you could have more than one graph, more than one plot open at the same time, here's how you can actually open up a new plotting window. This function here, win.graph, only works in Windows. If you're using a different operating system, the function x11 will work instead. And the nice thing about opening up your own graphics window is that you can control more aspects about how the graph is displayed. So the width is going to be 7 inches, the height is going to be 7 inches, the point size or the font size is going to be 10. So let me go ahead and execute that code. And once again, unfortunately, open up in a different plotting window or different monitor. And this is what we get. So now we have the default coloring of gray. I don't really see why we need to have gray bars, but that's what R uses by default. And notice how the x-axis nicely extends across the entire plot, where before the default, for some reason, it wasn't. And this just shows you that don't go with the defaults whenever you're dealing with a plot. Try to make the plot look nicer, more professional. And so this is what a better looking plot looks like. And I expect you to always try to make your plots look better in our class too. Okay, so we're on page 4 now of the notes. Let me get back there. So here's a question. What would a histogram for the relative frequency distribution look like? Well, what we have here is a plot of the frequency distribution, but what would the relative frequency distribution plot look like? In the end, it would look exactly the same. The only difference would be the y-axis would change. So now we would have, let's say, 30 divided by 142, 25 divided by 142, and so on, and we would put relative frequency as a label on the y-axis. So it will look exactly the same. Okay. Now, in the numerical summary section, we talked about this rule of thumb for the number of standard deviations that all data lies from its mean. Simply, it's about 2, maybe even 3 standard deviations. So if we just focus on the 2 standard deviations, we found that range, or that what the rule of thumb said was between 1 and about 19. Let's go back up to our plot. And we can see that 19 would fall right about here. We would see 1 would fall right about there. And guess what? What this is basically saying is all our data is essentially within 2 standard deviations from the mean, just like what the rule of thumb suggests. Yes, we do have a few observations that fall to the right of that upper bound, but if we were to go to 3 standard deviations, we would see that 23.63 would fall there. I don't remember what the exact largest value was, but we can see that we essentially got everything within that rule of thumb. So this is just a nice way to illustrate what that rule of thumb can do. Now, what I would like you to try on your own, or make sure that you understand on your own, is how could you have R actually plot this? This is a common thing that I ask students to do on various graded activities. And what I have here is the use of the segments function that will do the plotting for you. So what you will need to do is look up the help for the segments function to make sure you understand the corresponding arguments, execute the corresponding code to verify that indeed this rule of thumb is being displayed on the plot. Okay, so how could we just obtain the frequency distribution? I mean, it's nice that we have a histogram, and most of the time that's what you're going to be doing. You're going to be plotting the doing a histogram. You're going to be plotting the frequency distribution. But let's say that you want to actually see the numerical values of the frequency distribution. How can we get that? Well, it's not, unfortunately, as easy as perhaps what we would like, but it's not too bad in the end. So what I'm going to do is come back over here to R. So we've seen this code to do the histogram, and I'm going to put some results from doing the histogram into an object which I call save.hist, for the lack of a better name. And if I do that, note that the histogram will actually be drawn again, but also I have some information saved in save.hist. And how can I see what's in there? As we've seen before, use the names function. And here we go. So one thing that is saved in there is something called breaks. And hopefully this looks familiar to you. On page 1 of the notes, we saw these classes for each of the groups. And basically what this gives you is the beginning and the end value for each of the classes. So for that first class, greater than 2, less than or equal to 4. The next class or next group is greater than 4, less than or equal to 6. What were then the corresponding frequency counts? Well, let's put in counts instead. And here we go. So between greater than 2 and less than or equal to 4, remember we had 6 different days of wind speeds. And so using this information then, we could actually create essentially a table, but it's going to be in a data frame that contains the frequency distribution. Let's take a look at how to do that. So save.hist $counts contains all these frequencies, and if I were to sum them up, what I will get is the sample size of 142. And if I were then to take all the counts divided by the sum of all the counts, we now get these relative frequencies that we saw on page 1 in that table. Now, how about we round those values to 2 decimal places and put that in an object called rel.frequency. And here is information that we can use for the relative frequency distribution. Then I'm going to create my data frame using the data.frame function. I'm going to have a frequency variable that contains these counts. I'm going to have a relative frequency variable as well. And then I'm also going to have a variable that helps me determine, well, which class or which group each of these counts and relative frequencies belong to. I'm going to call it a variable called class. And then I'm going to get those groups from breaks in save.hist. Now there's one thing I want to show you before I execute that code. So we've seen before that if I execute save.hist $breaks, of course I get all those breaks. And this is actually a vector of values. And if I were to do left bracket, 1 right bracket, I would get just the first one. If I were to do instead 1 colon, let's say 3, I get 1, then TO2, 3 of these values in this vector. But if, let's say, if I want to see the elements in the vector without including a particular one, maybe let's say the first one, then I can use a -1 out in front of it, and now I just get everything but that very first value in that vector. And this is what we're going to do here for class, because you will notice, you can count on your own, that breaks here has one additional element, or it's one element longer than what's in counts, corresponding to these groups, these classifications. So I'm going to remove that first one. Let's put that all into a data frame, and here we go. So for the first class, we just got to remember, okay, it's greater than 2 and now less than or equal to 4. Frequency 6, relative frequency is 0.04. So that's how you can get your own frequency table, also your table of the relative frequencies too. Okay, let me see where we're at here in the notes. Okay, so now we have some questions starting on page 6. Okay, so how were these classes chosen? I mean, why did we go 2 to 4, 4 to 6, 6 to 8, and so on? Well, R has some algorithms that it uses to try to find the best set of classes. It's not a perfect algorithm. No algorithms are perfect in this kind of a case for a histogram. But it uses a particular algorithm. Now, what if we were to pick our classes ourselves? Let's say instead we chose to have only 2 classes. And so this is what the plot would look like in this particular case. In the end, this isn't very informative at all. It just says, oh, we got a lot between 0 and 20, and we got a little bit more than a little bit more for 20 to 40. That's all. So it's not very informative. So one thing that you have to think about when you're constructing histograms, and maybe you don't like the classes that R has chosen, is, well, I need to make sure that I have enough classes so that I can get a general shape of what you could say is the shape of how the values are distributed. Am I going to have a lot of large ones? Am I going to have a lot of small ones? Am I going to have some in the middle, and so on? So definitely you always want to choose more than 2. But then you might be thinking, well, how if I just choose a whole lot? Like here's another histogram that I drew now on page 7, where I have too many classes. Notice here we have a very, let's say, bumpy histogram where we go up, we go down, we go up, we go down, we go up, we go down with these bars. Again, this is not giving us as good of a picture of what these frequencies are telling us as what we had originally with our first plot. And so you need to be careful about choosing too many classes as well. So now how do you go about actually choosing your own classes rather than going using the default algorithm in R? Well, that's where there's an argument called breaks that will help you out. So if you remember the plot that I just showed you that had just 2 classes, here's how I would draw it. Let me get that plot back. So there's one break at 20. So that's what that corresponds to. I could also do, let's say, let's do 5 breaks to see what that looks like. And now I'm getting to basically a better looking histogram than what I had previously. R ended up choosing a little bit more breaks in the end. But this helps me get a general shape, general understanding of the shape of the distribution of all these wind speeds. Okay, so now we're on page 8. So is there maybe an easier way to find just the frequency distribution? And now I'll be honest with you that, generally speaking, you're going to be looking at histogram for most problems. But at times you do want to see a table of counts of frequencies corresponding to the classes. And I showed you some code to do that. What would be nice is if there was like a particular function R that would automatically just give it to you immediately. And as a way to illustrate then how to write a function, how about we create our own function to do that? Let me come back over here to 10 again. So I'm going to create a function which I call freak.dist for the lack of a better name. It's going to get the results from a function that I'm going to create. The first argument of the function is going to be the data. So I'm going to pass in my data set into it. And then I need to say, well, how many breaks do I want? So num.breaks. So I could pass in a value of 2. I could pass in a value of 5. I'm going to have num.breaks as an argument. Now, the actual name of the algorithm that R uses in HIS to come up with these breaks is called Sturgis. So since I am specifying here a particular value for num.breaks, I'm specifying a default for it to use this particular algorithm. Don't worry about the algorithm. I'll never ask you a question about it. If you want to know more about it, take a look at the help for the HIS function. But I'm going to give the option to a user to change how the breaks are chosen. But if they don't want to deal with it, then let's just go with the default that would normally occur. Okay, then I use a left curly bracket to say, okay, here comes my main part of my function. And I'm going to use a lot of the code that we just saw. Save.hist. I'm going to, what I'm saving into it is the results from the HIS function. Notice for breaks here, this is where num.breaks comes in. This could be a number or it could be, again, the default value. Then I'm going to find the relative frequencies, just like we just saw. And then lastly, remember the very last line of the function itself in terms of one complete statement is what's returned to the user after they execute the code. And what I'm going to return is that data frame, just like we had calculated before, that contains the frequency and the relative frequencies. So let me go ahead and run that. Again, in R's terminology, we have created our own function. This function is also an object as well. And then let's actually use freak.dist with our wind speed data. And here's our table. If I wanted to, I could have saved the results. Let's call it save.freak. And saved it into an object. Okay. So now bottom of page 8. Well, what about R Commander? Again, R Commander is a point and click way of using R. Could you use R Commander to create a histogram or create other plots? Yes. I'm not going to go through the details here, but I would urge you, or I do urge you, to take a look at the notes here. I give a kind of step-by-step process of how one would go about doing it if one chooses to do so. Okay, so that takes us to the bottom of page 11. So what have we learned about wind speed now? We've looked at some numerical summaries. We've now looked at some plots. What have we learned about it? Well, we've learned, for example, at least with respect to the frequency distribution here, that we seem to have kind of a slow runoff in terms of these wind speeds relative to we quickly go up to the most observed values for the wind speeds. We've also learned stuff about the mean. The mean, I think, was about 9 or 10. Let me just take a look at my previous notes on that real quick. So also what we've learned is the mean's about 10. The median was about 10 as well. We have a standard deviation about 4.4. And so we've learned some information about these wind speeds, and this was again over a 5-year period. We'll come back to this wind speed data set, or this example, a number of times now throughout the rest of the semester and look at more sophisticated ways of examining it. So I briefly mentioned something about skewness with respect to the wind speeds. And this term skewness is used to describe the symmetry of a histogram. So for example, let me just simply draw a histogram here. So we have frequency on the y-axis. On the x-axis we have, let's say, values of y, our variable itself. And let's draw in some bars, let's say. Now these bars should always be the same width. Unfortunately, I don't draw them very well here, but they are meant to be the same width. And so what we see here is, well, at least the purpose was, we have one bar that's kind of high, and then we have two bars at exactly the same height that's surrounded. Then we have two more bars that are exactly the same height that surround it, and so on. And so in this particular case, we have a symmetric histogram. And we would say the distribution of these counts is not skewed. However, we could have situations where we have left skewed or right skewed histograms. A left skewed histogram would be we have a longer tail on the left side than on the right side. What that means is our histogram could look like this. This was the opposite of what we saw with the wind speed example, where it slowly goes down on the left side, and on the right side, it quickly goes down to 0. In this particular case, the mean will actually be less than the median. So I would be surprised if maybe the median might be here and the mean might be here. Now, why is that? You should think about that. It has to do with the fact that we have, let's say, more extreme values. Oops. Remove that. I'm trying to get my highlighter out. Let's try that one more time. Maybe I don't have a highlighter up there. Let's see if I can pull one out real quick. There we go. We have more extreme values on that left side than we have on the right side. And what we learned was that the mean is more sensitive, meaning it will change a lot more. It will be pulled towards those extreme values, where the median will not be as affected by the extreme values. So for example, let me see if I can erase that. Good. Let's say instead of having this last bar there, suppose instead we have the bar right there. So we have two different scenarios where the bar is maybe here, or that last bar is there, and let's say just represents one observation. The median will not be affected at all by that, but the mean will now move towards that extreme value. So that's what we mean. That's what we mean by the mean is more affected by extreme values, or what we also call outliers. Now we could also have a right skewed distribution. And let's actually go back. See that? This for the wind speed is right skewed, because notice how it kind of goes down kind of slowly on the right side, where on the left side it goes up to that peak quickly. In this particular case, let's see now. The median was about 9.7 and the mean was 10.2. So notice how the mean, let me actually write that there, the mean is greater than the median, because these values out here are pulling the mean towards it, where they have less of an effect on the median. And so the term skewness is a way to describe what we just see there, or have seen there with this histogram. Notice I used the word tail of a histogram. Sorry, I should have defined that before. Basically, on the extreme portions of the histogram, far left, far right, excuse me, that's often what's called on the tail of, if you think of these, the distribution of these frequency counts. So here are some questions, and I've already answered those questions. Okay, let's move on to a new plot. This is one of my favorite plots. In fact, you're going to see a lot of my favorite plots in these notes. This is called a dot plot, and you may or may not have seen dot plots before. I think they can be very, very useful. In summary, what a dot plot is, a dot on a plot is plotted for each observations with respect to the y-axis. Often these dots are jittered, meaning moved a little bit in the x-axis direction to prevent overlapping. Dot plots are an excellent tool for comparing observations that fall within certain strata, let's say. In particular, let's look at the serial data. Let's take a look at the plot for the serial data first. So on the y-axis I have sugar. On the x-axis I have shelf. So shelf 1, 2, 3, 4. Remember, we have 10 observations per shelf. And what we see here is for shelf number 2, these dots represent the actual sugar contents. And we can see how they are shifted up in comparison to shelf 1, 3, and 4. And we were seeing those kinds of things happening earlier when we were looking at the mean and the median before. Also, what's interesting is that here we have some sugar values as well. But notice how we have a lot of high sugar ones that kind of correspond to what we had for shelf 2. But then we have some lower ones as well. And that's what ended up pulling down the mean. And the mean ended up being, if you remember, very similar for shelf 1, 3, and 4. Now let me do some erasing here. And lastly, I just want to point out, just to make sure, excuse me, that you see this. Let me get to my data here. So if you remember, actually let me just pull it up here. So let's take a look at the serial data. So let's take a look at shelf number 2, Rice Krispie Treats. Okay, so that was observation 11. It had a sugar content of 0.3. Let's go to our plot and find that. So here's 0.3. Oops. Fortunately, my pen is not working because I had the eraser on. So if I come over here to 0.3, essentially right here, or maybe right there, depending, maybe I didn't draw the line straight enough, is that particular observation on the plot. Now you notice how these plotting points here are moved a little bit, actually in a random manner, in the x-axis direction. This is what I referred to as jittering before. The purpose of jittering is to try to avoid observations from overlapping. So like what we see here, if I did not jitter, one might question, is that one observation because they would be overlapping, or is it 2 observations? So that's why it's always good to jitter your observations. Okay, so how did I actually do this plot? Let me actually come over here to R, or TinR. Well, the actual function itself, and I don't know why, excuse me, it's called strip chart. And the syntax is, you have an X argument, and that's where you put in information what you're plotting. So we're plotting the sugar values within cereal, and we're plotting them by shelf. Method equal jitter, that does the jittering in the x-axis direction. Vertical equals true, meaning notice how those points were in a vertical manner. If I had false, instead they would be in a horizontal manner. We will typically always do dot plots in our class in the vertical manner, and you'll see why shortly. PCH, if you remember, that corresponds to plotting character. Plotting character 1 is the open circle. Make sure you understand why we prefer to use open circles rather than closed circles, meaning filled in circles on a plot. My main title for my plot, y-axis label, x-axis label. If we run that, then we get the actual plot that we just saw. Okay. Okay, let me see where we're at here in the notes. So we've kind of answered those questions on page 14. Now, it would be nice if, let's say, that we could also put some numerical summaries on the plot too, on this dot plot. And so another plot that actually does do that in a graphical manner is what's called a box plot. I wouldn't be surprised if all of you have seen box plots before, but let's take some time to review what those are. Overall, I think it's easiest to illustrate what a box plot is through looking at an actual box plot first. So this is on page 16. Let me get my pen out here. So a box plot has a box on it. That's where the name comes from. And the box itself starts at the 25th percentile. I guess it's better to call it a rectangle instead. And ends at the 75th percentile. And inside the box, you're going to always see a line. And this is always going to be the median. Okay. Sometimes on box plots, although we don't have this in R, you will also see the mean plotted too. And so what this gives you is from the 25th percentile to the 75th percentile, and this is with respect to the x-axis numerical values there. What this gives you is basically it shows you where the middle of your observations are. Now also on a box plot you have some lines here. See that those lines that extend out from the rectangle? Those lines are called whiskers. And because of that, you will often hear people refer to these as box and whisker plots too. The purpose of the whiskers is that they are extended out to a place relative to this numerical axis where you would expect most of the observations to fall within. If you have any observations that are outside that range, as we have here, this is actually, that's for group 1. So I should have mentioned at the very beginning where this is a box plot that allows you to compare different groups. So we have any observations that are outside those whiskers. Those are often referred to as extreme values or outliers. Now, how does one determine how far to draw these whiskers out to? And one could use that rule of thumb for the number of standard deviations from the mean. However, typically with a box plot, you have let's say a different rule of thumb that's used instead. And instead, these values are drawn out as follows. Take the 75th percentile, add to it 1.5 times that 75th percentile minus the 25th percentile. Excuse me. So in other words, start here at the 75th percentile and go out this much farther. On the other side, relative to the x-axis numerical scale, this is drawn out, it starts at the 25th percentile. You subtract off 1.5 times the 75th percentile minus the 25th percentile. And again, the purpose is to do the same thing as the rule of thumb. It's just a different rule of thumb, I guess you could say, that one will look at. So that's what a box plot is. And as I draw on the box plot here, what you can see is a box plot's often used to compare, let's say, different groups of observations. Like, for example, with respect to the serial data, maybe it might be shelf 1, shelf 2, shelf 3, and shelf 4. Also, what it does, it helps you see a lot of the same stuff that a histogram would show you, in terms of here's where the middle of the bars, or the bars that have, let's say, the greatest height typically would be. And then, you might see some very small bars on the tails of that histogram. That's where the outliers are located. Now, how do you actually then draw the plot? Well, I'm never going to actually have you do it by hand. I mean, you could do it by hand based upon the information I just gave you, but I won't have you actually do it by hand. We'll just let R do it for us. However, if you want to see step-by-step directions, here's what the directions are. That is located on page 15 of the notes. Now, I do want to mention, before we actually look at how R does its plot, or how to actually do the plot in R, is that R does the plot a little bit differently in terms of how far these whiskers go out. Rather than going out as far as I've mentioned, instead what R does, it looks, okay, let's say the largest observation was 5 for group 2. And after doing my calculations of the 75th percentile plus 1.5 times the 75th percentile minus the 25th percentile, let's say right there, that might be about let's say 5.3. And when R will say, okay, this rule of thumb says to go out to 5.3, but my largest observation was 5 instead. So instead, let's just cut the plot off, or that whisker off right there instead. That's how R draws its plot. And it does a very similar thing then on the left side of the plot too. Now, I mention this because, of course, this is how R does it. But one of the reasons why I presented the plot originally a different way than how R does it is because, unfortunately, there's a number of different ways to do these box plots in terms of how far the whiskers go out. And so if you were to choose a different software package than R, make sure you take a look at the help for that corresponding function or procedure that draws the plot to make sure that you understand how exactly that plot's being drawn. Okay, so let's take a look at some stuff in R. This is again with the serial data. Okay. So what I like to do is actually do, and this plot is located on page 17. I like to do a side-by-side set of plots where I have the dot plots first, and then I have the box plots second, so that you can compare the two. And to split my graphics window into two different components for the two different plots, I can use my function called par. We briefly talked about that before. Par stands for graphics parameters. And the graphics parameter that I'm going to choose to work with here is this one called make frame by row, where I'm combining together one row, two columns of plots. In my first row 1, column 1, my first plot, I'm going to put the dot plot, just like what we saw before, and then I'm going to put the box plot. So how do I do the box plot? Well, instead of the X argument that you see in strip chart, Instead, there's a formula argument instead. And the syntax is put your variable that's going to go on the y-axis. Where are you plotting by? Shelf. Where is your data? It's in serial. What color do you want to fill in the boxes with? You don't have to choose a color. I chose light blue here. What's the title of the plot? Y-axis label, x-axis label. So let's go ahead and run this, put it all together, and let's take a look at the plot. And here we go. So let me jump back over here to Word so I can draw on the plot nicely. Okay. So let's look at shelf 2. Here's the median. Here's the 25th percentile. Here's the 75th percentile. Remember, it would be also the 0.25 quantile, the 0.75 quantile as well. Now, how far did these whiskers go out? Well, because there is actually no extreme values or outliers up here, I then know that how R shows that top portion of that whisker is it ended up being the largest observation. In a similar manner, R shows the smallest observation for the bottom. Okay? And so what we see here in this diagram is, notice how the center of most of the data points, again between the 25th and 75th percentiles, they are shifted up in comparison to shelf 3, 4, and 1. And we saw that same idea here, and we also saw that with some of our numerical summary measures as well. And so this is giving us more initial evidence before we do a formal statistical analysis that looks like there's something up here with respect to shelf 2 in terms of the sugar content in comparison to shelf 1, 2, and 3. Let's see here. So I have some comments. What you can do on your own is take a look at these 25th, 50th, and 75th percentiles. I found them quickly using the aggregate function, which we've seen previously. Notice how my fun, or my function I'm using, is the quantile function. And since with the quantile function I need to specify the actual which quantiles I want, I can also add a corresponding argument, probs, for that. And so what you can do on your own is, like, for example, for let's say shelf 2, verify, is the median equal to 0.42? Let's come up here. Yep, it looks like it is 0.42. Do that with the 25th percentile, do that with the 75th percentile as well. If you want to, you could also find, well, how far those whiskers would be drawn out if they were drawn out all the way instead of the to the maximum or minimum values. Now, one thing that's important to realize that when you do a plot like this, you may have a situation where the y-axis for this plot, the y-axis for this plot are not exactly the same. So if you wanted to do direct comparisons between the two plots, that wouldn't be possible. So instead, what you might need to do is actually control that y-axis with, let's say, the argument y-lim. And you can specify the minimum value, the maximum value, and make sure that both plots are drawn on exactly the same scale. Now, even a better plot, and if I were to do a box and dot plot, typically I will always do this plot here. I want you to take a look at the code on your own because it's very similar to what we just got done doing, where now I have the box plot and the dot plot plotted on top of each other. I think this is a really cool plot. And in this case, we only have 10 observations per shelf, but you can imagine other cases where you have more observations. And this really helps you look at both at exactly the same time. The key to actually doing the overlay of the dot plot on top of the box plot is to use the add equal true argument. Again, make sure you go through the code on your own so that you can see it. Okay, so now we're at the bottom, page 19. Let's take a look now at this wind speed example once again. And what I'm interested in looking at is, are there differences across the years for the wind speeds? Remember, we have 5 years worth of information. And so what we could do now, let me jump over here to 10. What we could do then is, there we go, is now how about we look at the mean, the standard deviation, maybe even the quantiles by year. So I can use the aggregate function once again, where I have a formula argument, and I'm putting what I'm trying to aggregate y, which is the wind speed. I'm doing it by year. My data is in wind, and the fun function that I'm working with is the mean. I'll just do the mean and standard deviation because it's easy here. And so what we see here, it looks like year number 2, the wind speeds went down a little bit. I don't know, I'm not an expert on wind speed. I don't know if this is like a significant finding that we have here, but that's kind of interesting. We also see with respect to the standard deviations, you know, we have some years that are have a smaller standard deviation than others. Well, let's take a look at this then with respect to a plot. Let's see here. Let's actually do this one. So this plot is on page 21. Let me just go to the notes on that so I can write on it. So here's now this box plot with the dots plotted over it. And so, you know, we see that this year 2 seems to be shifted down in terms of the distribution of these wind speeds in comparison to the others. It's not necessarily dramatic. I don't think it's as dramatic as perhaps what we saw with the serial data set, but we do see a little bit of a shift. We also see somewhat consistency between 3, 4, and 5, and maybe even year 1 as well. So year 2 seemed to be a little bit more different than, you know, some of the other years. That's kind of interesting to find out. Also, I do want to point out that look at year number 2. You know, like its minimum value and its maximum value are, minimum value is the smallest of all the years. Maximum value is almost the largest of all the years. And interestingly, the standard deviation is 5.02, which is very close to the largest standard deviation, which was for year 3, which had 5.08. Year number 4 had the smallest standard deviation with 3.4. And we can see why. You know, look at this. It seems the points seem to be more tightly focused than in the other years, or not as dispersed, I should say. And so, you know, we looked at the numerical summaries, but these plots also give you the same kind of information as well. And so you need to get in a good habit of, whenever you see a plot, you know, making comparisons like this. Think about it in terms of what the numerical summaries would be corresponding to them, especially when you're making comparisons. Okay. Please make a note of this part right here. I want you to look at this on your own with respect to what can happen with outliers when you actually do one of these overlaying of the plots. Of course, if after you look at it, you're not for sure exactly what I meant, you need to ask me about it. And here's something else I want you to think about. I'm not going to go over the answer here, but I'd be happy to address it at a later time if you ask. Suppose you were to do the same kind of plot that we just saw, but now the temperature for every decade from 1900 to now was included. Let me get a drink of water first. So for example, let's see, here's my plot. So we have, let's say, a plot for 1900, a dot plot or box plot for 1900 to 1910, 1910 to 1920, and so on. You know, what would you expect in terms of a trend for those boxes or those dots over time? Think of this in terms of global warming. Now do exactly the same plot, or think about exactly the same plot, but now do it with respect to every year rather than every decade. What would it look like? And again, and just to make sure this was clear, so you're plotting, let's say maybe the high temperatures per day in February, similar to what we saw with the wind speed example, where we were plotting the wind speeds per day. So what would happen, you know, in terms of the plot if you were to do it every year versus every decade? And maybe even relate that to what we were seeing with respect to histograms when we had maybe, let's say, too many classes versus a good number of classes or groups for our data. Okay, so we have a third example here. And with this example, I'm going to let you read it on your own. This deals with dividend yields of stocks. I actually took a random sample of 30 stocks from 2 different stock exchanges. And I did some comparisons using box plots and dot plots. I want you to take a look at this example on your own. Do note that we will actually come back to this example later in this course.